Hi, my name is Farhan Fauzi. I'm a PhD candidate at University of Florida. I'll be presenting our work titled ProXray, Protocol Model Learning and Guided Firmware Analysis. For problem and motivation, firmware analysis needs context, like architecture, memory layout, protocols used. Due to a variety of needs, firmware has to implement a variety of protocols. Complex protocols do not have formal specification. The USB spec is about 650 pages. The Bluetooth spec is about 3,000 pages. Once you have gathered the knowledge from these spec, we can start analyzing firmware to find out device behavior, detect implementation bugs, or identify malicious components. One of our main motivation was that real-world firmware already implements these protocols. If we can gather the knowledge from these, the analysis can benefit a lot. For example, we have two code snippets from both USB and Bluetooth firmware. This is vendor provided code. On the left-hand side, the USB code shows that the red marked fields are protocol relevant. First, there are values assigned to these protocol fields based on incoming or outgoing requests, and specific actions are taken based on the values of these protocol fields. Same thing in Bluetooth. Now, in both cases, the names of these protocol fields correspond to their exact names in their corresponding spec. And as you can see, it's very easy to find out protocol relevant fields from these code. Now, our model learning from known firmware can generate model from both source code and binary. We can learn from real-world implementations and practices. Our model learning is architecture agnostic. We do not need to dive into specifics of hardware architecture, and our learning phase is protocol agnostic. We have implemented it on both USB and Bluetooth firmware protocols. For design overview, ProXray works in three phases: model learning, field mapping, and model guided analysis. The first phase is model learning phase. At this time, we provide our model learning engine with a known set of firmware and a field mapping for those firmware as well. We specify in the address space of the training set which fields correspond to protocol relevant fields. Now, what our model learning phase essentially does is it records a constraint-based model to find out what specific values were checked for the firmware for the protocol relevant fields to perform any specific action. Once we have generated the model, we can move into our unknown space of testing firmware. Now, the constraint model is provided to our protocol field discovery engine. The first important task is to find out in the address space of the test firmware which fields correspond to protocol relevant features. Using our constraint model, we analyze the test firmware and find out in the address space of that firmware which fields correspond to protocol relevant memory locations. Once we have done that, we can move into model guided analysis. At this time, the provided mapping from phase 2 can answer user provided queries. Our model guided symbolic execution utilizes our constraint model to answer these queries. Now, for an example firmware with bad USB, which conceals HID functionality in addition to its reported MSC, which is mass storage class functionality. So to find out whether bad USB is malicious or not, we queried what functionalities does this USB firmware contain. ProXray was able to tell us, in addition to MSC, it also contains HID functionality. Now, for evaluation of our protocol learning phase, our heuristics perform 73.8 times speed up on USB, and we got a more than 100 times speed up on Bluetooth firmware. Our heuristics specifically focus on enriching our protocol model to gain more constraints from the protocol relevant parts of the code. For phase 2, accuracy of our mapping phase, we were able to achieve high precision in both USB and Bluetooth related protocol field mapping. And for Bluetooth, we achieved high precision for both HCI and LTCAP layers. Our phase 3 was functionality discoveries, where we can start answering queries after the mapping is done. So for this phase, we trained on MSP430 USB Despack, single functionality firmware only, so we can get type-specific constraints for each functionality. Once we have gathered that, we were able to analyze both Intel 8051 and MSP430 firmware to find out their functionality. Our precision and recall for both architecture is 100%. To summarize our contribution, we are able to directly generate protocol model from firmware using several symbolic execution, prioritization, and pruning heuristics. Once we have generated our model, we can automatically recognize protocol usage in the test firmware. From there, we can answer queries about the unknown firmware. We have applied our methodology to multiple protocols, both USB and Bluetooth, HCI and L2CAP layers, and we have evaluated on multiple architectures, MSP430 and Intel 8051. Thank you. If you have questions, you can ask me at the provided email address.